Okay, good morning, everyone. Any questions before we start? Okay, we look at that. 46. Okay. So we have the following integral x to the power 2 over to power 3 dx. Okay, all right. Ideas.
You can have four separate equations. You have a over x minus 2, b over x minus 2 squared, or sorry, only 3,
Yeah.
and b over x minus 2 cubed.
Yeah, we can do that. Can anybody think of another way? In this particular problem, it's very, very particular problem, which I think easier than the partial fraction decomposition. Or we can do it two ways. We can do it partial fraction, but we can do it in a slightly different way.
Can we use u?
Yeah, we can use u. What do you want to use for u?
X minus 2.
Right, we can use u equal x minus 2. In this particular problem, because, you know, when we learn something, it's nice to use it. du is dx. And when you are integrating, everything, when you substitute, everything has to become in terms of x. So this will give me x equal u plus 2. So we will have u plus 2 squared over du. So we can do that, this problem in this way, or partial fraction decomposition, but I think this will be easier. So this will give me u squared plus 4 plus 4u over u squared du. So finally, I will have u squared over u squared is 1, 4 over u squared, I'm splitting the numerator, plus 4 over u du. Now, if we had done partial fraction decomposition, we would have had.
Isn't u cubed supposed to be in the denominator?
I was wondering what's really wrong. 4 over, so it's going to be 1 over u. I will erase 1 over u plus 4 over u to the power 3 plus 4 over u squared du. Now, if we had done partial fraction decomposition, we would have gotten the same. I mean, if you done partial fraction decomposition, you would have 1 over x minus 2 plus 4 over x minus 2 to the power 3 plus 4 over x minus 2 to the power 2. We will have exactly the same thing. And now we can integrate. So we can do this problem in a different way because I think that's easier. This will give me the ln of u plus this one. No, I have to rewrite it as 4u to the minus 3 du. And this one has to be rewritten as 4u to the minus 2 du because those are not log terms. So finally, I will have ln of u plus 4 times 1 over minus 3 plus 1, u to the minus 3 plus 1, plus 4, 1 over 1 minus 2 plus 1, u to the minus 2 plus 1. And now we go back to our original one. I will have x minus 2 times 1 over x minus 2 squared minus 4 times 1 over x minus 2 plus c. Okay, so this problem, we don't really have to go to partial fraction decomposition. I think this will work. It would have been problematic if I had, the minute I would have had x plus 1 here, then I cannot use this approach. Partial fraction decomposition is the way to go. But because I don't have in that, I can work it out this way. Okay. So let's look at the other two problems quickly, and then we proceed. So I'll do 45 first, and then I will look at 76. 45, where is it? Okay. X squared dx. Okay. This is a typical partial fraction decomposition. There is no way I can do substitution in this case. So, and the numerator, the degree here is 1, degree here is 3. So we are safe because the rule applies in this condition. So we're going to first factor it out, but the problem is already given factor, so I don't have really to do it. And now, this is linear non-repeating. I said the order in which you put things doesn't matter. This is repeating. It's x and x squared. So this is going to be b over x plus c over x squared. And now I multiply across by the least common denominator, which is this term right there. Okay. And then we do that. If I multiply this by this term, I will get x minus 5 equal a over x plus 1 divided by this, I will be left with x squared plus b over x. If you multiply it by x squared times x plus 1, the x is, one of the x simplify, the 1 stays, and this will give me the x plus 1. Okay. Okay, which approach you want me to use? Do you want me to pick up value or expand this? What?
Pick a value.
Let's pick a value. 0 has to be 1, because if I pick 0, this term will go, and I will be left being able to compute the c. I will have minus 5 equal bunch of zeros plus c. Minus 5 of the back. And then the other value is, quickly, what's the other value?
-1.
Negative 1, because I will have those zeros, I pick up the a. I will have minus 1 minus 6 equal a, basically, plus 0 plus 0. So a is minus 6. And then I still have a b to find. I don't have any more values to easy values, because 0 will make those two 0 and minus 1. There is nothing else. So I can pick anything you want. Now, I usually pick something fairly simple. I pick 1 because 0 taken care of, I've already picked. So it's going to give me n1 minus 5, which is minus 4 equal a, basically, plus b times 1 times 2 plus c times 2. So now I substitute everything. So minus 4 equal minus 6 plus 2b. Now my c is minus 5. Let's give me minus 10. So I will get minus 4 equal minus 16 plus 2b, which will give me 2b equal minus 4 plus 16 equal 12, b equal to 6. And this tells me that my expression, that's very, very complicated expression, is equal to a. It means minus 6 over x plus 1. So we really broke it up into fairly simple terms to evaluate, plus the b, which is the 6 over x, plus the c over x squared. And I remind this is called partial fraction decomposition. This process called partial fraction decomposition. Now, what we are left with is the integration part. So the antiderivative will be equal to minus 6 times the antiderivative of 1 over x plus 1 dx plus 6 antiderivative of 1 over x dx. All those are simple now. Minus 5, and this is a square, so I rewrite it x minus 2. That's not a log term. That's not a log term, be careful. So finally, I will end up. This is x plus 1. If I put u equal x plus 1, du will be dx. So this one will not be a problem. Plus 6 ln of x. X to the minus 2, we've done it like a million times. This is going to give me 5 times 1 over x plus c. End of the problem.
I have a question.
I'm listening.
Will there ever be a case where we can find all the values of like a, B, and C?
No.
Like, or no? Okay.
No, no way. Unless the degree of the numerator is larger.
Oh, okay.
That's where problem will come up. Then you can, I mean, there will be, it's hard to explain, there will be infinitely many. It doesn't work. Mathematically, it's not correct. I mean, this decomposition mathematically fail. And I will try to give you an idea why it fails. Mathematically, this fails. It doesn't hold if the degree here is larger or equal to the degree of the denominator. Otherwise, it will always give you answers. No way out.
All right. Thank you.
All right, so we're going to look finally at number 76 and see what this is about. It's cosine theta over d theta. And this is sine cube minus 4 sine theta. Okay. All right, so quickly, what do you see? Quickly, when you look at this, what do you want to do?
Can we make sine u so then the cosine would cancel out
Right.
when you?
It's like screaming at you, basically, and telling you make u to be the sine because the derivative is right there. So we have to start with this step. So u equal to the sine, then the du is the cosine, theta d theta. And by doing this, this will be transformed into a cosine theta d theta. That's my du. And this is 1 over u to the power 3 minus 4u. Okay. Now we look at this. This is a rational function. So slowly, you should always ask yourself, okay, what type of integrand? But that's how you're going to be able to solve those problems when you have when you have to use any strategy there is. So you look into this and say, okay, this is rational. It means they have a polynomial of degree 0, and that's a polynomial of degree 3. So the way we deal with rational is partial fraction decomposition as long as substitution fail. And there is no substitution inside here because there is a 1 in the numerator. So we're going to do that. Now, the first step in the partial fraction decomposition is to factor the denominator completely. So here I can factor out my u, leaving me with that. Equal. Am I done?
No.
Can I start decomposing?
U plus 2, U minus 2.
Exactly. We cannot start the decomposition till we factor completely. And this is not factored completely. So this will give me 1 over u times u minus 2, u plus 2. And now we're ready. And that's a simple scenario because this is going to give me a over u. They are all linear. There is nothing repeating. Over u plus 2. Now I multiply across by the common denominator. I will have 1 equal A. So the common denominator is u minus 2, u plus 2. So if this will be left with u minus 2, u plus 2, plus b. If I multiply by that, I will be left with u times u plus 2. And the c would leave me with u times u minus 2. And now there isn't much into this because I can take u to be 0, because here the factors are u plus 2. So I take u0, u2, and u minus 2. So u0 will give me a times minus 2 times 2, which give me a is minus 1 over 4. Then u equal 2 will give me 1 equal 0 plus b times 2 times 4 plus is 0. 1 over 4. And the last one is the minus 2. 1 equal 0, 0, c times minus 2 times minus 4. C is 1 over 4. And
Shouldn't
then,
be 1 over 8.
did I do this mistake across? No.
Yeah.
The first one is correct though, or I did a mistake here. No, I'm safe. All right. So now let us just integrate. So the expression 1 over u to the power 3 minus 4u du is the same as the following. A is, okay, instead of writing the a here, it means 1 over au. And the b is 1 over 8 times 1 over u minus 2. I put the constant in front because to make the math easy for me. All right, it's equal to minus 1 over 4 is a constant. Antiderivative of 1 over u is the ln of u plus 1 over 8. Antiderivative of that is also a log term. It is the exact log because if I put t to be u minus 2, the dt will be du. And at the end, I will have that. Finally, I go back to my original variable, which is the sign, and I substitute in front of the sign. Okay, so I will have ln of sine theta plus 1 over 8 ln of sine theta minus 2 plus finally 1 over 8 ln of sine theta plus 2 and of the problem. Okay. Okay, can I move on? So today, what we're going to start today. So all our decomposition are based on the factor we have in the denominator. This will really decide for us how we decompose. So today we're going to start basically the last piece of the factor of the denominator. And we're going to take the case where the denominator has a quadratic expression that we cannot factor. But before this, I have to talk a little bit about quadratic expression. So before the last case, we're going to introduce the idea of quadratic. What's a quadratic expression? So a quadratic expression, like linear, is ax plus b. Quadratic expression is an expression of the form ax squared plus bx plus c, where a is not 0. Okay, that's what's it quadratic. Now, the thing is about quadratic is that some expression of this form, we can factor them. And some, we actually cannot factor them. So that my question, we're going to address at the beginning, which expression can be factored, which cannot be factored. So the question is, which quadratic expression can be factored? And which can't? Factored means write them as product of two terms, as linear terms, can be factored. So that's really our question. Okay. So I'm going to start to motivate where the idea comes from. I'm going to start with a simple expression. Suppose I give you this quadratic, x squared minus 5x plus 6. Okay. And a question to you, can we factor this expression? It means, can we write it as a product of two linear terms? Yes or no?
Yes.
Yes. So let's see. This could be factored as. What are the factors quickly?
X minus 2 and x minus 3.
Ah,
wait.
2 and 3 will do. Okay. So x minus 2, x minus. Okay, so it can be factored very easy. So suppose now I ask you the following question. Solve this following quadratic equation. Is it an easy problem or hard? Solve this. Because we can factor it so simply, we can solve it also very easy way. So solving this exactly like solving this product. So this will give me that x equal to 2 and x equal to 3. So if I have a quadratic expression and I can factor it, then we can solve the quadratic equation very easily. So if we can factor, then we can solve the equation, the quadratic equation that corresponds to the expression. We can solve the quadratic equation. Okay, so if we can factor it, we can solve it. So now the idea is that over the real, so we're not working with complex numbers. I know some of you have seen complex numbers. We're just working with real numbers. No complex in our scenarios. So if we can factor it, we can solve the quadratic. So the idea now that if we cannot solve the quadratic equation, then there is no way we can factor it. So because if we can factor it, we can solve it. So if we can't solve, so if we cannot solve the quadratic equation, ax squared plus bx plus c equal to 0, then we cannot factor it. Then we can't factor ax squared plus bx plus c. So if we cannot solve it, we cannot factor it, because if I can, I would be able to solve it. And now the question is addressed to you. When we cannot solve a quadratic equation, under what restriction we cannot solve a quadratic over the real? Anybody remember?
Isn't it when there's just no numbers that could solve the equation?
That's correct. When does this occur? If you use your quadratic equation and you try to solve it, the quadratic formula, and you try to solve the quadratic equation when you don't have a solution as a real number.
If B is positive and C is negative.
There is something, no, that's not correct. Anybody remember back high school?
When what's under the square root sign or the discriminant, is it called, or something like that?
Yeah.
If it's negative or
Right.
if it's below 0.
0 is allowed. No, 0, you can do it. You can solve it if it's 0. You cannot solve it when the discriminant is negative. So remember, if you use the quadratic formula, so let's recall. To solve, when you use the quadratic, you don't have to write this. I'm just trying to remind you. To solve, if you use your quadratic formula, if the discriminant or this term is negative, strictly negative, then basically you cannot solve it. So you cannot factor it, because if you cannot solve it, you cannot factor it, right? So if the discriminant or b squared minus 4ac is negative, then you cannot factor the expression. So we're going to put the rule when factoring an expression over the real numbers is not possible. So we're going to have the following rule. Okay. So given an expression, a quadratic expression, ax squared plus bx plus c, different from 0. Then we have the following. If b squared minus 4ac is negative, strictly negative, then the expression cannot be factored. Can't be factored. Okay. So we look at the expression. If this is negative, it means there is no way we can factor it. If it's positive or equal to 0, positive or equal to 0, then we can factor it. Then the expression can be factored. Can be factored. We can actually factor it. Okay. And this is the rule. And the rule is the following. So we can factor it as follows. Now, sometimes you look at it and you know how to factor it, but sometimes you look at it and you don't know how. But there is a rule we can use. It can be factored as follows. If R1 and R2 are the solutions of the expression of the equation ax squared plus bx plus c equal to 0, then that's how we factor it. To be factored as follows. The a times, these are the factors, x minus your first solution, x minus your second solution. So, given any expression, if b squared minus ac is negative, then the expression can't be factored. If b squared minus 4ac is positive, then the expression can be factored, and we factored it as follows. If you look at it, we know how to do it, fine. If you look at it, we don't know how to do it, then we go after the solutions of the quadratic equation. Once I know the solution, we're going to have 2 of them, then ax squared plus bx could be written like that. So this is really the rule. So let us a little bit practice it before we finalize the last sub case in our decomposition. So in each expression, I want you to tell me, can we factor it? Yes or not? So the question is, can we factor? All right. Suppose I give you the following expression, x squared plus 4x plus 5. Based on the rule we did, can this be factored? So the way you're going to do it is, you're going to evaluate the b squared minus 4ac. Evaluate it slowly. B squared, coefficient of x, it's 16, minus 4 times 5. This is equal to minus 4 negative. So can't be factored. regardless what you try, regardless what you do, there is no way you can gonna write this as a product of two linear factor like this. Okay, another example. If I put x squared plus 4x minus 5. And the question is, can we factor it? And in this case, if I compute b squared minus 4ac, even though it's simple, I will have 16 plus 20, which is positive, we can factor. And in this particular scenario, factoring is easy because I think the 5 and the 1 will do it. And this should be plus minus. Okay. Now the last scenario. So this can be factored, cannot. This can. So a small change will change the picture. Okay. The last scenario. Suppose I give you x squared plus 4x plus 2. Okay, can we factor this?
Yes.
Yes, because
Yes, because
b squared minus 4ac is 16 minus 8. That's positive. We can factor it. What are the factors? Can you see them?
I have a question real quick.
I'm listening.
Why is a considered 4? Why is a considered 4 to be 4 in the b squared minus 4ac?
No, it's the 4. A is 1 and the c is 2.
Okay.
So it's 4 times 2, which is 8.
So how did you get? Oh, okay, I see.
Got it?
I missed that 4 there.
Oh, no.
Yeah, I
problem.
do. Thank you.
All right, sure. So can you factor it by looking at it? Can you find two numbers when you multiply, you get a 2, and when you add, you get a 4?
I don't think so.
However, we can factor. And what is the rule that I just gave you? The only way we can factor this is as follows. We find the solutions. Once we find the solution, that's the factorization. So if you cannot see it, it doesn't mean you cannot do it. If you cannot see the factorization, doesn't mean you cannot factor, you actually can do that. And that's really how we factored. That's really the idea here.
Can you keep that up for a sec?
What I did.
Thanks.
Okay. So once I know the solution, whether I can spot them, because when you factor, you're actually give yourself the solution. But if you cannot see them, we have to use the quadratic equation. Okay, done? Are you guys done?
Yeah. Thank you.
How can we factor? We have to go after the solution. So what are the solutions? So we're going to find the solution of the equation now. Plus 2 equal to 0. And we use the quadratic formula because we don't know what the solutions are. So that's going to give me minus b plus or minus the square root of 8 basically, because that's the discriminant here, divided by 2. And if we do a little bit of math, and if I don't mess it up, I will get two solutions, minus 2 plus or minus, I think we should be left with the square root of 2. And it means we have two solutions. One is minus 2 plus the square root. And one is minus 2 minus the square root. So what does this mean for us?
I have a question.
Yes.
Did you get the square root of 2 by taking out 8 from the 2?
Yeah. I took square root of 8. I wrote it as 4 times 2. Right? So which is 2 times the square root of 2. So this became 2 square root of 2. And then I factored out the 2. Then I'll be left with that. Okay?
All right, thank you.
Okay. Now, it means what are the factors? Equal to A is 1. So A is 1. And the rule tells me these factors are x. Sorry, I'm going to write it bigger. X minus the first solution, which is minus 2 plus that, x minus the second solution. So it's not we cannot factor, it's just that we don't know how the factors are. It's so hard for us to see that those are the factors. Means if you multiply this out now, it's a nightmare, I won't do it. If you multiply those out, you're gonna get x squared plus 4x plus 2. So that's how the factorization works. Now, not being able to do it does not mean you cannot do it. It means you don't see it, okay? All right, now that we're done with this, we're ready to start the last case, okay? Your quiz is on Brightspace, get going.